So now we'll take a look at some examples in PSCAD and in Simulink for how the line modeling gets implemented. And this first example is showing how we can set up a coupled pi model. And so what I mean by the coupled pi model is you have this scenario here we go. You have this scenario where you have series impedance. There's also mutual coupling between these phases, between phase AB, BC, and AC. And then you've also got the capacitances. You have the interphase capacitance and you have capacitance to ground. We're putting half the capacitance on the source side and half of the capacitance on the load side. So the inductive coupling is there, but it's just not shown in this diagram. And so anyway, what this model is set up to do, it's set up where you're applying the source. Now you can see there's a time constant on here where it's ramping up. And then this is all three-phase. And so this is a three-phase module. This is three-phase source module. And you can basically wire everything up in three-phase instead of drawing each phase out. And then these are three-phase meters, which are designed to show P, Q, and also the voltage in this case. So when we're running this, what the difference in these measurements should give us is the power losses due to the line. So this is the resistance. And then the difference in reactive power is the reactive power requirement of the line, which is mostly going to be related to I squared times X. The capacitance is going to offset that a little bit, but mostly this is going to consume reactive power. And we put a load on here as well so we can get a little bit of a voltage drop. So anyway, when you set up the line model, then what you have is you have these windows that come up when you double click on the pi model, and then you have a name for it, you give it the frequency, and you give it the line length. In this case it's all in meters. And then you would enter in data in different formats. And so in this particular case I've chosen the positive and zero sequence format, and that's why in my MATLAB example in the previous overhead lecture, that's why I formatted those results the way I did, because these are in terms of values like ohms per meter, which are kind of weird units, but and then this capacitor reactance is in terms of mega ohm meters. So I had to kind of do some adjustments on those values to get them into the correct format. So let me go ahead and pull this over from PSCAD, and I'll go ahead and put this up online as well. So when you actually gonna run this, then this is the pi model circuit. Then we could actually execute this, and then basically see the simulation crank up. Yeah, it's running. It just takes some time. And that just kind of shows you it's running, and you can see what we're calculating is we're calculating these steady state values from the meters. If you left click on this element, you can see the inputs. And what you have the option of doing, you have the option of putting this data in different formats. And so basically you could put this stuff in like in a per unit format. You could put this information in terms of these values like I've done in terms of positive and zero sequence values. You could put this information in surge impedance format, and we'll talk about in the next lecture about the basically the traveling wave model. So that's kind of where this information could come from as far as having surge impedance and travel times. But there's different sort of formats you can put this data in, whether it's like in ohms or in per unit. So anyway, if you guys are doing three-phase, and say if it's at the lower frequencies, this would probably be the type of model to use. If you're doing faults, if you're doing like the capacitor switching, this probably would even work like for the transit recovery voltage. For these types of events, you could use this coupled pi model. The go back to the slides then. So anyway, this is what you would do when you're using this particular model. Is if you go to models, basically you can see you've got these pi sections you could choose from. There's another place you can do is we can go to the master library. And then what you could do is you could pull from these different icons right here, and you can pull in from the master library like the symbol for the pi equivalents down here in the lower right hand corner. I don't have enough screen space here to show this properly. It's kind of hard for me to manipulate this. But anyway, you basically drag and drop this element onto the screen, and you have your coupled pi section model. Okay, so let's suppose you didn't have a piece of MATLAB code on hand or didn't have somebody else's program to do these computations. And how would you do this? And the way you would do this in PSCAD is you use a program called T-Line. And so basically what T-Line is, it's a standalone program which basically pulls these values in from a PSCAD screen, does a calculation, and then spits these values out. And you guys have probably noticed that what you have when you run these programs is you'll see like a GF42 or GF46 directory showing up. That's basically because this transmission line program is a standalone program, and what it does is it basically spits the results out in this directory. And so there's a file there that's going to get generated as a result of this called tline.out. So anyway, here's an example of using the transmission line parameter calculations using T-line. And what you do in this case is you kind of pull a generic model in to the PSCAD main screen. And if I were going to double click on this model, what you see is you see these different blocks. And these are different blocks that you drag and drop in from the component menus. And so you can see you've got this definition canvas right here. This is where you put in like the number of conductors, and this is where you put in the line length and the fundamental frequency. You've got this Bergeron model option. So basically this is kind of like the basic PSCAD model that's used for a lot of your more general transmission line calculations when you want to model traveling waves. You also have another thing you drag and drop to get the distances between the conductors. And then there's a drag and drop for modeling the ground. So it's kind of weird how this happens. Is basically it's like you're dragging and dropping all these elements in. In your case, I'll post an example up online so you guys could reuse this if you ever need to do this in the future. But basically you have to drag and drop all these elements, and then if you want to display all this stuff in a certain format in an output file, then you have this additional options thing you have to kind of drag and drop on the screen. But anyway, what you'll see is if you then look at the line model settings, then you see you have all these windows that are associated with this, where all this data that you're entering in is kind of showing up here. And so what you would do, again, you still have to put in the length of the line, you still have to put in the number of phases, the fundamental frequency. And then what you would also put in here is you'd also have to have information in here about the conductors. So you notice that you have the conductor information. This is a 336 conductor. This is the main phase conductor. You have information about the radius and the stranding and everything else. In this case, you would put a DC resistance in. So you have that type of information. And in another window, you can see that you've got all this XY position information as far as the distances between the conductor pairs. You've got other data you're entering in as far as the ground wires in this case, and so we have like one ground wire that's underneath the three-phase conductors, and you'd have an XY position associated with this. And so really what you have here is you have a pretty complicated tower model in terms of the different phases you have and the ground wires you'd have. And this is kind of characteristic of, for different versions of EMTP, how you'd enter in the data. So all the different versions of EMTP would have this type of support program for you in order to calculate these values. All right, so I think, yeah, and then this would be the output of what we have in the T-line file. And so when you were going to go ahead and run this, I'll post this as well. This is basically just a simple example file that you can use as a reference in the future. You can think about this as being one step beyond the coupled pi model. It involves a little bit more computational overhead. It should give you some better results. If you're working at lower frequencies, it probably won't make much difference, but if you're working at higher frequencies, like looking at lightning strikes and stuff like that, and then you really need to have this particular type of model, because this is actually modeling the traveling waves going back and forth on the line that you have for the high-speed events. But anyway, if you're going to go ahead and you're going to left click on this, and you could see all these different screens that you need, and again, you kind of have to drag and drop the right screens from the model library. So it's a little bit of a pain, as it's sort of unconventional. And then what you do is you basically then click on each of these items, and then you go ahead and enter in the data as needed. So you see in this case, you got the conductor data, and you've got the coordinates and everything else you could enter in here. Okay. Now, if you want to look at some detail in terms of what's in these files, like I said before, depending on whether you load it in the Fortran 4.6 or the 4.2 compiler, basically what you would see is these different files showing up in here. And so if I were going to open up the T-line out, open up with Notepad. Oops. Yeah, here we go. Anyway, PSCAD line constants program output file right here. So this comes out of T-line. And basically what it does is just spits out this data based on the input in all sorts of different formats. And so again, you can get the positive and the zero sequence values. And what I did is I entered these values in kind of consistent with the input to my MATLAB example, because I wanted to see how closely they corresponded. One thing that's going to be different here is the way you enter in line resistance, because before, when I did my MATLAB code, I assumed I had the AC resistance, where in this case they start with the DC resistance, and so I'm not exactly sure what kind of fudge factors they use to convert that to an AC value. It's probably somewhere in the documentation, but these come up pretty close. And you can see what it does. It gives you the 3x3 impedance matrix. You can notice here that this is not exactly set up where you have equal mutual values and equal self-impedance values, because again, this is not symmetrical construction. You have different spacing between A and B as opposed to A and C. You have this shunt admittance matrix. In this case, this is given in terms of Y. So what I calculated in the notes was X. You have to invert that, and that gives you Y. And then it calculates a bunch of other values we'll talk about later on in terms of all these modal quantities. So anyway, it spits out a lot of interesting type of information, and basically what it does is it creates a file that PSCAD reads back in to populate the model. And so every time you change the line parameters, you have to rerun this T-line program. Okay, so that's that. Let's go back to the slides. All right. And then finally, for the cable modeling, I just kind of dug around some of the examples that were available up on the PSCAD website. And they did have an example where they're energizing a transformer through a cable. And so what they were looking at the inrush phenomena and kind of what difference the cable model would have on the inrush. You could see what's going on in this case is they're using three-phase formats. This is like a three-phase source model. But then what they want to be able to do is they want to be able to access each phase individually in here. And so what they use is kind of what we call like a splitter. So then this would give you actually access to each of the three phases. And where you would use something like this, like if you want to put like a single phase fault in there, then you can have a splitter in there to give you access. So that just enables you to go back and forth between three phase and single phase. But anyway, for the cable layout, somewhat similar in that you have to drop a cable canvas down to specify the fundamental frequency. You can see this case it was 50 hertz. You would put in stuff like the length of the line and number of conductors associated with it. I'm not sure in this case why this is 0. I didn't create this particular case. Then you got the Bergeron model that you're using. And in this case, what we're showing here is we're showing one cable, the details of one cable, and then you have a system where you have 3 cables that are symmetrically spaced, cables 1, 2, and 3. And so what you would do then is you would kind of go through the same thing before, is if you use a T-line model, then you're basically putting all this information in about the cable. So here we're entering in data for cables 1, 2, and 3, etc. We're putting all this information here about the radiuses and the thicknesses, and so this is kind of the physical information about the cable. But you're getting all this information, you're putting in resistance information, and it's really quite complicated. And as far as different sort of things you can enter in here, it's much more, a little bit more sophisticated than the stuff we went through in lecture. So they're adding a few more bells and whistles in here as far as the model. But basically, when you run this, then it'll make use of the T-line model, and it'll go ahead and calculate the pertinent types of parameters. And so anyway, I'll post this up on the Moodle site, but this is just something I pulled down from the PSCAD page as far as one of their examples. And like I say, you can enter all this detail in here. So anyway, you could do both overhead, or you can do cable systems, either way. All right, so this is what's available in PSCAD. All right, so you can also do some of this in Simulink. The Simulink models aren't quite as sophisticated as PSCAD, but they've got some interesting cases in the examples. And so one example is this 3-phase power triphase line. And we'll talk in the next lecture of what's this distributed parameter model, but what they're doing is a comparison between lumped pi segment models and distributed parameters. And what they're trying to show is if you want to get the more accurate results you get with this distributed parameter, you can think about this as like the Bergeron style model. What you can do is you could model this with lump parameters, but you just have to have multiple segments of these lump parameter models. So they just kind of split it in two and show that if you have 50-kilometer segments, I can kind of get about the same results. So this is a line energization. What they're doing is they're just energizing phase A in this case. So note you have a source impedance in this case. What's interesting is when you're doing transits at higher speeds, instead of using an RX in series model, you typically use an RX in parallel model, because what you want to do is you want to kind of use this to kind of represent the surge impedance seen by traveling waves going in the toward the source. So anyway, this is set up where you're kind of doing a comparison, but what we're really just kind of concerned about in here is what's kind of going on in phase A and phase B when I close in phase A. And what we could see is we could see the setup for this. So in this case, what they're doing is they're entering in the positive and zero sequence resistance, the positive and zero sequence inductance, and the positive zero sequence capacitances. Slightly different units. I mean, they're using units in terms of kilometers in this case. Again, you give it the line length. So you can see it's a lot simpler than the PSCAD input. And then what you could see is you can go ahead and you can actually see the transit results. And so think about what you should see. So if I go back to this case, if I have a line model, and let's suppose there's not much voltage drop across here, then if I energize this with phase A, and it's a sinusoid, let's say at 60 hertz, eventually what I should see on this side is I should eventually see in steady state a sinusoid, roughly the same voltage magnitude on the receiving end. But look what happens in this case when I energize. Basically what happens is it's like I get like a voltage doubling effect. And so I see that when I switch this on, after a little bit of delay, the voltage doubles, and then it kind of rings, and then it goes into steady state. And so what we're seeing here is we're seeing a switching transit. This is very common. What you also see in phase A is we see some voltage on the adjacent phase because of the mutual coupling. But anyway, the way you can kind of think about what's going on is if I've got this line model, recall it's got some capacitance and it has some series inductance, right? So what has to happen? Well, those capacitors need to charge up, as well as the series inductance to some extent, right? Because everything's starting at initial conditions of zero. So between the inductance and capacitance in the circuit, what you're going to see is you're going to see this transit, basically. Just like you do any other sort of transit, we could actually do some calculations where we switch a source on. We could have basically modeled this with two capacitors and probably an inductance in this case. And this is basically what you see. And so this voltage doubling effect is something we'll see when we talk about distributed parameters. But this is definitely an overvoltage again. And then what you would need to do to damp this out is maybe use surge arresters or some pre-insertion resistor on the switching, or maybe control the time we do the switching in order to keep this receiving end transit from jumping up to such a high value. So you can go ahead and I'll put this up on the Moodle side as well. I mean, if you guys want to go ahead and run this, you can go ahead and run this model as well. Let's see if I have this convenient here. Yeah. So anyway, this is what it looks like. Basically, like say they're comparing the two different model types. And if you type in run on here, then what you could do is you can see what kind of impact this would have on the voltage at the receiving end. Takes a little while to run. Yeah, here we go. And anyway, you can see here's the transit part, and then eventually we get into steady state. Okay, so then one other example in Simulink is you do have ways you could actually calculate these values, which are in the Simulink Power GUI. And so if you were going to go in and click on this and look at tools, you can see that you have this utility called RLC line parameters. And so this is like Simulink's program for calculating these quantities that would go into the line model. And so instead of having to figure all this stuff out from scratch, what you can do in here is you can go ahead and you can put in things like the frequency, base frequency, earth resistivity. Here you have the XY information for all the phase conductors. You have all the XY information for the grounds. You can go ahead and you can put all the conductor information in here. And then basically you could set this up where it'll auto-populate your Simulink simulation then. So again, all these programs simply have all these tools for kind of facilitating this. And so anyway, let's close this down. If you need this in Simulink, then they have an RLC line parameter program in there. This looks to me like it's set up more for overhead, but basically you can see that it computes all these different matrices and it calculates series impedance and the line capacitance. There is also a cable example in here, and so what they do in this case is, they're just kind of showing how to use the model. And there's another program that's built into MATLAB called Power Cable Parameter. And so if you're going to execute this program, this is actually what this looks like under the mask. It basically is this lump parameter representation. Now, if you look at this, you'll notice on here you've got all these different inductances, and this is just basically to start with. It was a fairly simple system. And so basically what you can do is it just kind of shows in here, how you could model more complex types of configurations. And then when you run this power cable parameter program, then what it has another input where again it captures all this information about the cable itself and the number of strands and resistivity and all the different diameters and everything else that we talked about in the theory section. So anyway, this is why I said at the very, very beginning, it's probably unlikely you're going to have to do this very often. You have all these utility programs that are available to do all these calculations, but then what you have to make sure of is you understand the inputs. So you have to understand what all these distances are. And that's kind of why I spent time going through this, is you kind of see at least in the formulas where these values would go, and just make sure when you utilize these programs that you're entering all these values in correctly. Otherwise, obviously, you're going to get the wrong results, right? Okay, so that's all I got on the line modeling, and what we'll be covering in the next lecture is what we call distributed parameter models, which is how do we actually do the line modeling where we have very high-speed transits associated with line switching and faults and also lightning strikes.